share my...
It has to be recorded, okay? So it's a pleasure to have Angel on more with us for the third lecture on invariant manifold in celestial mechanics and astrodynamics. Please, Angel.
Okay, thank you. Today I will talk about invariant manifolds of, it will be a bit more concrete than yesterday, last day. So I will talk about fixed points of maps, which are equivalent to periodic orbits of flows and invariant tori. So essentially, today I will work with applications of how to use a linear approximation to grow the manifold. This is a quite simple way. In fact, it is used in many works to use the linear approximation to grow the manifold. And I'll show that it's enough for several applications, for many applications. Okay, the use of high order expansions for the manifold is left for the next session, which is the last. And there we will discuss how situations in which high order approximations are needed and how we obtain them. So in fact, in last lesson, we also discussed how to use linear approximation to the manifolds to control a spacecraft. But the goal of today will be to use this linear approximation to grow a manifold to study transport problems. So, well, let's start, for the simplest case. So let me assume I have a discrete dynamical system, smooth, as differentiable as needed, analytic. That in the application, it will be a Poincare map, okay? But for the discussion, we don't need to specify that, it's simply a map. So it has a fixed point, and this point is, let's say, unstable. So it means it has a real eigenvalue, which is larger than 1. And for the moment, I will assume that this is the only one with this condition. Okay, this implies that there exists a 1D unstable invariant manifold that is tangent to this eigenvector of this eigenvalue at the point. So then it's very easy to write the linear approximation to the manifold at the point as a straight line going through the point P0 and with the vector of direction B. And of course, this is only accurate when the parameter of the linear approximation is small enough and sigma is small enough, and the error is of order of course, is sigma squared. Okay. Well, comment. That comment will be also used in the next class. So in principle, the true manifold can be written in many forms, for instance, in parametric form. And this parametric form is not unique, since a line can be parameterized in many ways. So you can use different parameterization for the same curve. So we'll choose a good parameterization. People in differential geometry likes, for instance, the arc parameterization, but here we will prefer a different parameterization which is compatible with dynamics. So, the parameterization we use in the manifold satisfies that when the parameter is 0, we are at the fixed point, and when the parameter is different from 0, the sigma is different from 0, then the dynamics on the manifold is to multiply by the eigenvalue. Okay. Well, as a comment, a small comment, the manifold has two sides that are, as lambda is positive, the sides are, let's say, disconnected. One corresponds to sigma larger than 0, another one to sigma less than 0. That's okay. Well, another concept we need is the concept of fundamental interval. This is for each side of the manifold. So is the piece of manifold between a point on the manifold and its image. So this fundamental interval is not unique. You have one for every p. And the point is that if we know a fundamental interval for one side of the manifold, then we can grow the full manifold by simply iterating backward and forward the map, the dynamics, on these intervals. Okay, that's very... So usually all the methods that wants to compute global manifold, want to compute a manifold for a very big piece of the manifold, they somehow use this remark. So they use a method to get a fundamental interval that can be, there are several, it can be a high order method or linear approximation or whatever, and then to go outside of the validity of this approximation where they have obtained the fundamental interval, they use the dynamics to move out. Okay, so that's what we will do. So let's see the idea and then let's see an example. So the idea is, okay, assume I work with some level of accuracy, 10 to minus 12, 10 to minus 14. So this is my linear approximation to the manifold, the eigenvector, the point, sigma is the parameter. So let me look for sigma 1 such that this point, this is sigma 1 is a value I will have to find. So that's this point and its image by the map is small enough. Okay, the idea of doing this is that then the segment that goes between these 2 points, between sigma 1 and sigma 1 lambda, is a fundamental interval with some level of accuracy, which is of the order of epsilon. And an initial guess for the sigma, because this is a linear approximation, so it's something close to a square root of epsilon. That's the idea. Okay, so you want to produce a fundamental interval. It will be a straight line. We'll take it from the linear approximation, and we have to do it that close enough to the point. That's the main drawback of these things. You have to do it close enough to the point. So this means that if you want an accuracy of epsilon, you have to choose it somehow at distance square root of epsilon. Okay, so let's continue. Once this fundamental interval is known, then to propagate the fundamental interval, a natural way is to produce, well, a simple, there are several ways, but a simple natural way is to produce a mesh of points in the interval to propagate them forward in time. Okay, the density of the mesh depends on each case. So it depends of how the manifold will bend or etc. Of the level of accuracy, how dense you want the mesh. You can interpolate on the mesh. There are lots of tricks you can put on that. And I mean, a good reference for this is this paper by Simon is at the end of the references that discusses how to put points and how to control how these points are expanded. And another comment, which is interesting, is that in the case I'm discussing, as lambda larger than 1 is the only real eigenvalue, bigger than 1, this manifold is attracting near the point. So in fact, during the first iterates, the error perpendicular to the manifold is not growing, but being reduced. Okay, because the manifold is attracting. So in fact, this is a trick that sometimes is useful to prove the existence of the manifold, to write a sort of fixed point and prove that you have the manifold there. But of course, when the manifold moves away from the point, this can change and the manifold cannot be attracting any longer. So you want to control how the error of the iterates grows. In case you want to know, I mean, you have to propagate the manifold for a long time or for a long piece of the manifold. There are several tricks, but a simple one, so I'm mentioning the first, is to compute at every iterate, to also compute the Jacobian. So the Jacobian measures the many things, among them how the error grows. I mean, that's the mean value theorem, if you want. Okay, so if you keep accumulating this product, the norm of this product is an upper bound of the factor of growth of the error. So in some critical circumstances, this can help to keep track of the error and to decide that if what you have is reliable or not. I mean, if you have problems with the accuracy with linear approximation, you might want to use nonlinear approximation to the manifold, and that will be discussed on Thursday. Well, for the stable manifold, you can apply the same ideas to the inverse of the map. Okay, so I mean, the inverse of the map for discrete systems sometimes can be difficult to compute, but for Poincare section, it's very easy. It's a matter of integrating backwards in time. So it's very simple. I mean, in celestial mechanics or astrodynamics, to have the map, the Poincare map, and its inverse. Okay, so let's do an example. I'll use an example during all these days. It will be the same example to simplify also the presentation, which is the bicircular problem. The bicircular problem is a modification of the restricted three-body problem that we already discussed in the first lesson. So here is I'm assuming that Earth and Moon revolve in circular orbits around their center of mass. and that this center of mass moves around the sun, which is, let's say, in the middle, in a circular orbit. Okay, so we take, as we are going to work near Earth and Moon, we take as origin the Earth and Moon barycenter, and we take the same axis as the restricted free-body problem. So Earth and Moon lie on the x-axis, the perpendicular is the y and the z, such that everything is a positive-oriented system. So in the reference is the sun that turns around. That's the angle of position of the sun. This model is introduced in the 60s, and well, there are several references about it. Okay, this is an autonomous Hamiltonian. So because of the perturbation of the sun, the 5 equilibrium points of the restricted free-body problem are no longer equilibrium points. But I mean, a simple application of the implicit function theorem tells that if the effect of the sun is small enough, they become periodic orbits with the same period as the sun in the model. So the model can be written in Hamiltonian form, and it's quite common to write it in this form. So you have two terms in the Hamiltonian. One is the restricted free-body problem, that's the classical one, plus a perturbing effect, which is this one. Okay, that depends on the position of the sun, this angle, and also here I forgot to write RPS. RPS is the distance from the particle to the sun. I'll write it before giving the slides, the formula. I've just realized that I haven't written, but that's the potential of the sun. So, and that's a Coriolis term. Okay, so then L3, let me focus on L3, is change from a fixed point to a periodic orbit. So I'll work with the planar problem. So L3 in the RTBP is a point of a center saddle type. Saddle is quite mild. In the VCP, this becomes a periodic orbit with the period of the TS. TS is, let's say, the period of the sun. So, I mean, times the perturbing term. So in that way, we get an autonomous map from 4 dimensions for R4 to R4, and we look for a fixed point near L3 by means of a Newton method. So we get it, and that's, for instance, the orbit. I mean, the fixed point is here. I haven't marked it, but it's one of these 2 points is there. And that's if we do an integration to show it, it takes this form, and that's the unstable eigenvalue. The stable is the inverse, I haven't written it, and there are 2 elliptic directions. Okay. Well, and we are interested in the unstable direction. So let's simply discuss it. So let's simply apply what we were doing before. So we compute the stable and unstable eigenvectors at the point. Let me choose this value, sigma 1, that's the square root of epsilon I was mentioning before. So let's check. I mean, if at this distance, here I'm checking, I mean, how invariant is the straight line, comparing the straight line with the dynamics, the true dynamics of the Poincare map. So I get these approximate values. Plus and minus is because you have 2 sides in the manifold. So I've checked both. So they are close to these values. So, well, if that's enough, that for my example is enough, it's simply an example. So we can go to the next step. I mean, if these were too big, I should reduce this sigma 1 a bit. If I don't need that accuracy, I can increase it a bit. So to grow the manifold, let me take a fundamental interval using sigma 1 and to grow the manifolds. It's a matter of doing some iterates. So here is L3, this point here. Red is unstable. So I'm taking a very small fundamental interval there and I'm doing some iterates. The eigenvalue is around 3. So every time I multiply by 3, so in 10, 15 iterates, I'm completely away from the point. Multiplying, I mean, the 3 to the 10 is already a big number. And for the stable, which is the blue, yes, the stable is red, yeah. And the stable, which is the blue, so I use the inverse map. So the inverse map, the differential is the inverse of the differential, so the eigenvalue is the inverse, so it's again 3. So essentially, I can use almost the same program, but changing the map by the inverse of the map. And that's what I get. So in the middle, there's more or less the Earth. Here is the Moon. And I've plot only a piece because in this moment, I don't have any purpose than to show it. I mean, in the next example, I will have a purpose. So then I will have to compute with some requirements. But this is simply an example. Okay, so these things show that it's, let's say, intuitively quite simple, and you can improve it a bit using interpolation in the manifold. You can do little numerical tricks, but essentially that's what you need to know to do it. Okay, so let me change to the same thing, but not for fixed point, but for the next kind of invariant object, simple invariant object, which is an invariant curve. So again, I'll assume I have a smooth diffeomorphism with an invariant curve. I will not discuss omega is a frequency, which is irrational. So I will not discuss the existence, because what I'm doing is I'm assuming there's an invariant curve there, and I want to use the manifold, the stable and unstable manifolds, to do something. I'm not assuming anything special, although in the example, because this will be the Poincare map of a Hamiltonian, I will have some properties. But for that part, I don't need it. Well, sometimes in some situations, you can also consider this. Okay, this corresponds to, for instance, a Poincare section of something that depends quasi-periodically on time. So all the ideas are very, very similar, but as my examples will be the bicircular, and when I do the Poincare section, it gets autonomous, I'll focus on the autonomous case. Okay, so, well, finding rotation numbers, that's not the topic, so I'll go very fast. There are lots of methods, and essentially they boil down to represent the manifold in some parametric form, typically a Fourier series, and then to impose conditions to find the coefficients of this Fourier series numerically. So a very simple, probably the simplest one is to simply to impose the curve to be invariant and to solve the system by Newton method. But there are other methods. It's not the only one. Okay, so, but I want this. We can control the error, checking how invariant the invariant curve is. Well, the second point is about the stability. When I had a fixed point, I simply had to look at the eigenvalues and eigenvectors of the differential at the point. Well, here I need to do something a bit more elaborate, in the sense I don't have a point, but a curve. So in principle, if I linearize the dynamics near the curve, which means take a small displacement from the invariant curve and expanding, so I see that the linear dynamics, the propagation, is not by a constant matrix, as it happens in fixed point, but with a matrix that depends on the angle. So, I mean, the linear dynamics is represented by this matrix, which let me call it A here. So this is the linear dynamics around the invariant curve. Well, these are literature on this. These are called linear quasi-periodic skew products. They have been studied from many points of views and with different purposes. And essentially, I have to extract from this the unstable direction if I want to compute the manifold, or a stable, or whatever. So it is, well, I mean, if you have used a method that already gives you this manifold, you can skip this part. But if you don't, you only have the invariant curve and you need those, you can compute them in a very simple way. So I will introduce a concept. I'll do that part also quite fast, because it's not the goal. So in principle, a system like that is called reducible if there exist changes of variables of that kind, of this form, that when these changes is applied to this, the system becomes this form, that's the B, but B is now constant. If such a change exists and we know it, so we can do that, then from B, it's very easy to get everything, because we simply have, I mean, the system is decoupled. So I only have to look at the spectrum of B, eigenvalues and eigenvectors, to know the eigenvalues and eigenvectors of everything. So if I take an eigendirection on B, I can send this eigendirection through the change, and have the eigendirection from the initial system. So it is quite simple. Okay, how we can find this change and to know if it exists? Well, let me mention a very simple method, which is to write this condition as an eigenvalue problem. So that can be done in several ways, but I mean, a natural one is that an eigendirection is a direction that when I apply the dynamics, I get lambda, That's the unstable eigenvalue. I don't know. I'm looking for lambda. That's the eigenvalue I'm looking for. For the next point, I mean, this function is here for this. This goes here. So that's the linear condition for a manifold around the torus. When I apply the dynamics, I rotate on the torus by omega, and I grow in the direction by lambda. That's the condition. So this is an eigenvalue problem that we can solve numerically. I mean, this can be written in the form of the so-called transfer operator, and there's some theory about these operators. Okay, but I won't do it in the sense that what the only thing we need is to solve the eigenvalue problem. So here I've written some properties to explain how the spectrum of this operator is, but let me skip it. It's not the goal. So I mean, the spectrum is a bit special. It takes the form of circles, but let me skip it. So I mean, I put a reference in case you want to read about this spectrum, and there are other references inside. So it is okay. So what's the final goal? To solve this eigenvalue problem numerically. Okay, we discretize as we did before with the invariant curves. That's something that so this becomes a big matrix. We run an algorithm for find eigenvalues and eigenvectors. So we get the spectrum. Okay. Well, we can discuss the accuracy. There are some tests for accuracy. I will also skip them because I will focus in the result. There are some norms to measure. So let me jump to use that to the situation we are interested in. Okay, so what's the situation? I have a smooth discrete dynamical system. I have an invariant curve. And I have an unstable direction. Okay, so I'm assuming I know this. I know the invariant curve, I know the unstable direction, and I know the unstable eigenvalue. Okay, well, the situation is similar to the one of the point, but with this rotation added on the invariant circle. So as before, I mean, if I apply the dynamics on a point of this form, so this is an invariant curve. Sigma is a parameter, undetermined parameter. That's the eigendirection. If I apply the dynamics, this is Taylor with respect to sigma. I cut to second order, so I get this first term of Taylor because this is the invariant curve is exactly this. The next term is the action of the differential on the unstable direction. So that's this thing. So that becomes that. So this means that, sorry, that's, oh. What? Can you see the screen?
Yes, yes.
Yes? Okay, yeah. No, sorry, it's my calendar telling me that I have to teach at 7 and it changed my screen. Okay, so this expression shows that this thing here is the linear approximation to the invariant manifold. Okay, so in other forms, this expression, that's a parametric form, linear approximation to the unstable manifold, the invariant curve, given by phi. Of course, I mean, this is a cylinder, but of course it is only accurate when the parameter is small enough and the error is order of sigma squared. So this is only valid close to the invariant curve. So here we can extend the concept of fundamental interval that in this case will be fundamental cylinder. Okay, so in general, if I have a manifold written in parametric form this way, a fundamental cylinder is a piece of the manifold of this form. Okay, so sigma 1 is a given value for sigma, and this is lambda sigma 1, that's the eigenvalue, the unstable eigenvalue. For the angle, we take the whole angle. So this is in fact, is a cylinder, I mean, a bounded cylinder. It's not unique. For every sigma 1, you have one. And as before, if you know a fundamental cylinder, you can apply your dynamics on the cylinder and to grow the full manifold. It's the same concept, okay? But simply now the fundamental, let's call it set. Before it was an interval, and now because it's not only an interval, because I have a torus on the basis, I mean this, so it becomes a cylinder, okay? Okay. Well, we can check, I mean, as we are going to use first the linear approximation, we can check how invariant is our linear approximation for several values of sigma. So we can compare how the prediction between the linear dynamics and true dynamics. And if this is small enough, then the manifold, we can call it, I mean, good for our purposes. So we want to choose the cylinder as far as possible from the point, but on the contrary, we want it to be accurate. So these conditions compete and we have to choose a good condition. Of course, I mean, there are situations in which linear approximation is not enough. There are several reasons for that, and that will be the talk of Thursday. But let me keep going with the linear approximation. Okay, so, well, this means that I have a parametrized of a fundamental cylinder with an accuracy of order epsilon. And usually sigma 1 is close to a square root of epsilon as before, and for the same reasons, because so I think it's clear. So let's do an example of that. So again, let me recall you the bicircular problem. The example, by the way, is taken from a paper by Begoña Nicolás, who is attending also the course. So here, the goal is to study transport in the Earth-Moon system. So we will include the effect of the sun in the bicircular model. And we will use the invariant objects near L3 as a skeleton for this transport. That's so in principle, L3 is replaced by a periodic orbit. We already discussed that. We compute that periodic orbit. This periodic orbit is sent as saddle. So, and then in the center direction, you have a family, Cantor family of invariant curves that also have this saddle. So this object is the one that we will study to see how these manifolds organize transport in the Earth-Moon system. Okay. Well, so here I have a family of invariant tori. So for the flow, this tori has two frequencies, the exciting frequency of the sun, the same for all of them, and a frequency that comes from the restricted three-body problem. Okay, we will work as usual in the Poincare map. So instead of a two torus, I'll have an invariant circle with some rotation number. And then we will apply the techniques we mentioned at the beginning. So I have a Poincare map. So I will impose an invariant conditions. I will write my invariant curve in Fourier series. I'll impose a condition, and I'll find the coefficients by a Newton method. Okay. So the advantage of this method is that very simple. The main inconvenience is that the matrix of the Newton method is full, and in some cases it can be large, but it's not in this case. Okay, in this case, I mean, these invariant curves are quite nice, so I don't need to do anything special. Okay, the number of equations is, in the worst case, hundreds, and hundreds is I mean, for today's computer is nothing. So we do a continuation method to compute not a single curve, but all the family. We check for the accuracy, blah, blah. So that's the family of invariant curves. Here is L3, where my mouse is. That's the Earth. So at the beginning, they are nearly circles, so a few Fourier modes are needed. And when we approach the Earth, they become more twisted, and then it's when you need more and more Fourier modes. So I mean, the last use around 200. Okay, but still we are covering a big piece. That's how the invariant curve of the curves behave. So that's the distance to L3. That's a parameter measuring the distance, and that's the frequency. Here you see a maximum, which is something, I mean, very nice for the dynamicist. But I will not discuss that. But I mean, that's an interesting place to study. Okay, but no, that's not the goal here. Again, I have to solve, I have to find the stability. So I'll write the eigenvalue problem, and I use a routine to solve it. So I find eigenvalues, eigenfunctions, blah, blah. And here is a plot of the distance to L3, and that's the eigenvalues. So I'm only plotting the, well, in fact, I mean, this torus has 4 eigenvalues, is an invariant curve in R4, but these 4 eigenvalues, there are 2 ones. One corresponds to the tangent direction to the invariant curve, the other one to the direction of the family, and the other 2 are 2 real eigenvalues, one the inverse of the other. This is between 3 and 3.5, and that's the inverse. And that's what happens when you move away from L3. So I mean, the most unstable becomes less unstable, and and the opposite for the stable. Okay, so we use our linear approximation of the invariant manifold as before, and we write explicitly a fundamental cylinder. So we can mesh the cylinder, and you can propagate forward and backward the manifolds. Okay, to see. Okay, that's an example. So here is L3, where my mouse is. Okay. So the green is the stable manifold. It has 2 sides. The red is the unstable, or 2 sides, and that's how they grow. So how they this is for an invariant circle close to L3. Okay. So that's the kind of dynamics they have. So you see they move around the system, and after some time they move outside. Here, I mean, it is interesting to mention that this model is Earth and Moon and Sun. Okay, the Sun is very interesting when you have things entering and exiting the Earth-Moon system, because when you move a bit away from the Earth-Moon, the Sun is the one that commands the trajectories. So, I mean, it is, I mean, the entrance, I mean, to go in and go out from the Earth Moon with or without the Sun is very different. So we want it with the Sun. Okay. Okay. So let's study the dynamics. So now we want to see transport. So what kind of transport? So, well, let's first explain how we'll study the transport. So one problem that we have when you study this kind of systems is visualization. So this dynamical system is a discrete system in 4 dimensions. So to draw what happens in 4 dimensions is not trivial. I mean, even in 3 is sometimes a bit complex, but to display what happens in 4 is not trivial, and well. So the advantage of this manifold is that we can simplify visualization. So a thing we can do is to take a fundamental cylinder, to take a measure of points on the cylinder, and to put a color on this point in the cylinder according to the fate of the orbit that starts at this point. So for the unstable, we will propagate the orbit forward, and we put a color to this pixel according to what this orbit, I mean, the place this orbit is going. And for the stable, we will propagate backwards, and we put a color according where it comes from. Yeah, so let's see what kind of plot you get. So this is a torus close to L3, to the periodic orbit of L3. So up is, let's say, unstable. Let's start with up. I don't know if you can see my mouse here. So up is unstable. And then is the 2 plots are the 2 sides of the manifold. So here I'm putting colors saying that this purple means that this trajectory collides with Earth. Collides with Earth means that reaches Earth's surface. So we, I mean, when the distance to the Earth, because I mean, in this model, Earth is a point mass, but when the distance to the trajectory to this point mass is equal to the Earth radius, we assume you have collided. So this purple means you have collided with Earth. There's little points here in that side, but not in this side. Red means you have collided with the Moon. So you have more collisions with Moon than Earth. Yellow means you exit the Earth-Moon system. Or black is that in the piece of manifold we have explored, you are still moving around the Earth-Moon system, but you have not decided what to do. Maybe you will stay there for longer, maybe you will collide after a while. So this is for the unstable. this is for the stable. Okay, there's something you see that the plots look very similar, is that we have a symmetry. There is something I haven't mentioned. I mean, this is a particularity of this system. So in this system, we could use, for instance, here the symmetry seen very clearly. So I could have computed half of the things and to use the symmetry to produce the rest. Okay, I haven't done that, but although it's perfectly possible. I mean, I not use the symmetry because I didn't want to use any specific property of the example. And second, that if I don't impose the symmetry and the symmetry is not obtained, it means I'm doing something wrong or there's a strong propagation of error. So that's what you get. So we can change the torus and can keep these plots. So this is a different torus. That's the distance from, so this is only the unstable. The first two is the unstable of this tori, that's the distance to L3. And that is tori that is far away. You see that the plot is being deformed as you are changing. That's so, and that's the same thing, far and far away. So here it's more black. It means for the time we have been doing the explorations, it has not decided, but you see a bit of everything everywhere. So in principle, this suggests the following. So let me stay here. So if we choose a torus, let me go back in which I have a stable and unstable. So this means that from a torus, this is a single torus. In the unstable, I can go to the moon, right? And from the stable, I can come from the Earth. So this means that this torus can act as a relay for a travel from the Earth to the moon, because a piece of its manifolds backwards in time of the stable manifolds goes to the Earth, and a piece of the unstable one, looking at the future, goes to the moon. Okay? Well, that's not a good idea, in fact, because, I mean, if you think a bit, using invariant manifolds of that kind for a trip, it means the trip will be long, because when you approach the torus, you will stay a lot of time moving around the torus till you don't exit, or you do a little maneuver to exit from the unstable manifold, and that's not useful for a manned mission to the moon. But if you look at the reverse situation, that's more interesting. So let's discuss the reverse situation. For instance, I mean, it's known that, I mean, moon craters have been produced by impacts, and these impacts eject material at different speeds. And also is known that some lunar rocks are found on Earth. So, I mean, it's accepted that part of the material ejected from the moon by impacts, after traveling in space, arrives to the Earth. I mean, very small pieces are born in atmosphere, but not so small pieces can reach the ground, and so we can find them. And here the traveling time is irrelevant, we don't care. Okay, so, well, in fact, we have manifolds connected to the tori in L3 that in the past they have the moon, and in the future they have the Earth. So let's give a look at that. That's an example of transport, natural transport of the solar system. Okay, so here are examples of orbits that start on moon surface with a suitable speed and crash with Earth. So here, I mean, we played to find several. I mean, the more you approach a torus, here you see the torus. I mean, the orbit, it's clearly seen that you spend a lot of time very close to the torus. So these trajectories are very close to the manifold, not exactly on the manifold. I mean, if you are exactly on the manifold with zero error, you go to the torus of L3 and you stay there forever in this model. So, but if you choose it very close, so you stay a long time moving around and then you fall on Earth. If you move it, if you choose it not so close, maybe you don't stay that much time. So here you have, and also, well, that's the example I have. Well, this is another example, not the one I just shown. So let's do study this a bit more. So I want to do two things. One is to study this a bit, how robust these connections are. And the second part of the robustness is to see what happens in the real system, because this is simply a toy model. Yeah. So, but First, let's see how robust these connections are on the model. So for that, let me choose a trajectory. That trajectory is simply found taking a piece of manifold that lands on the moon from the stable. You look at the velocity, it arrives to the tori, and then with a bit of tuning, you make it to connect with the manifold that goes to the Earth. So you get this trajectory. I want to see how robust it is. Okay, so let's do something. So the result of is this plot. So let me explain what this plot is. So this trajectory is at the center of the plot. It's a point at the center. Okay, it's a single point. So it's, well. So we take the velocity vector. So we fix the starting point on the moon, and we're going to apply the velocity vector. Okay. With the velocity vector, as this is a 2D system, we change the angle of the velocity vector and the modulus. So in the middle, we have this is the angle, the corresponding angle of the velocity vector is in the plane. So a vector in the plane is one angle and one modulus. So we change the velocity and the angle. Okay. And we launch the orbit and see what happens. And what happens is the following. So if we decrease the velocity, so we get everything red, which means that the particle falls back on the moon. That's logical. If you don't have enough speed to escape the moon's gravity, if I reduce your speed, the ejecta goes up and then falls down. So that's the. Okay, we are interested in the purple lines, which means you are arriving to the Earth. The purple is this thing here. So you have some pieces, you have some open regions. So not exactly, I mean, the point is in the middle. Here you have a pixel, it's simply a pixel. I mean, you have to think that and that's true. I mean, you have a connection between manifolds, you have also sensitivity with respect to initial conditions. So if you change a bit, your connection can change completely. But the point is that as you have the structure, the invariant structure connecting, and not by simply the manifold of a torus, but all the manifolds, all the torus have manifolds with this connection. When you perturb, you find others. So you have some amount of connections. Okay, let's play a bit. That's with another orbit and with another orbit. And you always have these purple bands here. That corresponds to, let's say, domains, because that's open domains of trajectories that will land on Earth. So you have some level of robustness. So next, well, that's another example, different orbits. So next, let me discuss what happens when you try to repeat that for the real system to see how robust your manifold or your model was. So, oh wait, there's another applications. I mean, you can use that for transfer. So that I will skip it. We can use it to transfer satellites, but I put it here with a reference, but I won't discuss it. So let's go to this. So let's try to check with a best model. So in principle, as a best model, we'll take the solar system as an n-body problem. So we take Earth, Moon, Sun, all planets. They all interact between themselves and with the particle. And the initial data, we'll take it from GPL. We will use ephemeris DA405, which is not the last one, it's not a modern one, but it's quite accurate. And let's see what happens. I mean, there's a step in between that I will pass very fast, which is a change of coordinates. You have to change from reality to the model. That's a bit tricky. It's not difficult once you know it, as many other things. So you have to do a change of coordinates that includes a scaling, because Earth-Moon distance that is constant for me in the model is not constant in reality. So you have to rescale Earth-Moon distance by changes of a scale, and I have to do a rotation to fix Earth-Moon line on the x-axis. So I have to do that. It's a bit tricky, but not difficult. So let me go through it. And let's discuss this. Okay, so I will start from worse to better. Okay, so some people like better from worse, but I think I'm optimistic, so I'll go from worse to better. So this is the plot, the first plot I put. That plot here is that plot here. Okay, the one that I wrote. And that's the same repeated from using the realistic model. So if you compare them, you see a lot of purple, which is nice. So you have collisions. But if you compare the plots, well, here you have these lines, this curve. You see, there's this curve here that seems to be here. You have some similarities, but it's nothing astonishing. Okay, let me use the second of the examples. That's the BCP, the one we have computed with the manifolds, that the, let's say, realistic. So this is more similar, right? So, I mean, you see the same patterns, especially in all these P's, here and here. Okay. Well, so this means that the fate of initial conditions in BCP and in reality is similar. So our prediction of transport using manifolds is quite accurate for taking into account how simple the model was. So, and that's the last one. So this is the third of the example, that's the fourth. So still you hear like a sort of shift. So everything you see a sort of like this has been expanded and compressed. And that one is fantastic. Okay, so here there are two consequences. So one is that, well, not bad for the model, but there's a second question: why some are so good, like these two, and some are not so good? So why it happened? So could we guess before, I mean, in advance, which one was going to be better? Well, the answer is we think yes. So the answer depends on the moment we do the change of variables. Okay. And at the moment we do the change of variables, so we have to choose a date for the change of variables. I mean, for the BCP, dates are periodic. Everything repeats every period of the system, but that's not true in reality. So our system is not periodic at all. So when I choose a relative position of Sun, Earth, Moon, and so ever in the real system, because I'm taking that from JPL, so I have a different Earth-Moon distance. So I mean, I have a very different Earth-Moon distance. So in the first, that was the Earth-Moon distance. That's the second, the third, and the fourth. So in the fourth, the Earth-Moon distance was almost the average one. So here, when I do the scaling to make the Earth-Moon distance, the scaling is almost 1. And that's not here. The scaling here is different because I have to, here in the third, I have to enlarge, I have to multiply, and in the fourth, I have to reduce. Okay, so I have to shift velocities. And that somehow fits with the plots. Yeah, so I have a shift in velocities, which is clearly seen here and in the others. Well, I don't have this shift, sorry, in velocities in this last example, because it's the scaling is 1. So, well, I mean, that was the example I wanted to do. I mean, this is done only with linear approximation of the manifolds. So I've used this example to show the linear approximation of the manifolds, although in 2021, today, you can do better than that. Is still a good tool in many situations and very easy to use. So here I put some references that I was citing. So it's and the only thing I mean to finish is that although linear approximation can do the job in some situations, it's not enough in some others. And that will be the topic of my last talk on Thursday. So thank you very much.
Thank you. Let's applaud this wonderful lecture. Very good. So some question? Questions? I remind you that also on Thursday we will start 1 hour early, 1 o'clock here. That will be 6 o'clock in Europe. Okay. So question. So I have a small question. When you say, page 46, what the tuning, how do you do in practice the tuning? If this is a real, it's just switch the engine when you make the.
Well, no. I mean, the tuning is simply, I mean, the manifold arrives to the moon. The stable, I mean, you propagate the stable backwards. It cuts the moon surface, so you have the intersection. So then, I mean, you launch it, you launch it back, and due to the numerical errors, the orbit does not arrive exactly to the torus, but it goes for one of the two manifolds when it arrives to the point. So if it goes the one you want, that's fine. If you not, you move the last digit in the other direction and you have it. I mean, it's not very sophisticated. I mean, you can do it very sophisticated. I mean, if we had to transfer a spacecraft to do something, we have to do much better. We have to do much better on this. But I mean, to show that rocks can reach the Earth, to do complex calculations with high accuracy to find a rock going to the Earth, that's not true. It's not going to happen. I mean, the rocks arrive to the Earth if the connection is easy to find. It's very, and that's what happens here. You simply play, you launch a few conditions, and that's it. You get everything. So essentially, you can look it in the reverse. So when you have the point on the moon surface, you have the direction, you do a mesh, you launch it, and then you produce this plot, and you have the trajectories too. So it is not a matter, I mean, that's different from the case of working with a spacecraft in which you want to do something very specific and you have an engine and you have to do a maneuver. Here, the goal is to show that, well, this is a path. We are not claiming, we do not claim that this is the only path for a rock to reach the Earth, for a moon rock. That's not the claim. The claim that this is one option. Okay, and the good thing is that, I mean, for a dynamicist, I mean, for me, I mean, it's a nice way because I have an invariant torus with manifolds, a family invariant torus with manifolds connecting Earth and Moon. And that gives you a trajectories, lots of trajectories that goes from Moon to Earth. You also have the reverse, but the reverse is much, much more difficult. There are much less, I mean, the number of trajectories is much reduced. And also the problem for a Earth rock to reach the moon is that it has to escape the atmosphere, the friction of the atmosphere. Yeah. So, I mean, the impact should be huge. I mean, to send a rock outside the atmosphere, which, and this does not happen in the moon.
Thanks. A second, I stopped the recording.